Hey guys, it's Campbell. Been a while. Sorry about that. It's been a sort of a long quarter. So today I want to talk about something that you may encounter in higher math, which is a specific type of function notation. So you are probably familiar with your typical function notation. You were probably introduced to it in about 8th or ninth grade, and that is something like y equals f of x. Or you may see, of course, like f of x equals, and then some polynomial term, trig term, sine x plus x squared plus natural log of x plus 3 to the x, something like that. So this is a typical function notation for single variable functions, which there are a lot of course, and you dedicate a whole year to studying that in pre-calculus and algebra. So so this is your basic function notation, but there is another type of function notation which you will be introduced to as you further your math careers. And there's no real name for it, at least that I can find. If I do find someone giving it a name, then I'll come back and correct this. But what this notation looks like is something like this, where you have you might call it the name of the function, the call of the function. Typically we use f of x. In linear algebra, you will use a lot, but for now we'll stick with f. And that is, you'll see f colon, and then you'll see something like this. You'll see this scripty r, and then you'll see something like this. What exactly does this mean? Well, we're going to cover that today, and it's really interesting. So yeah, let's get into it. So first of all, we need to understand a little bit of basic set theory. It's nothing too complex, but you need to know that a lot of things in math can be generalized as sets. And so we can call the real number line the set of all real numbers. And so that's all that this scripty r is it is the set of all real numbers. And so, yeah, you can think of that just as the number line, and all the way towards that end, you approach infinity. All the way towards this end, you approach negative infinity, and you might have 0 here, and you might have, I don't know, -3 and 0.4 and, pi. And so this contains every single real number. And so that is every integer, that is every rational number, that is every irrational number. Every number, every real number is on this plane, all right? And again, that is denoted by r, that special type of r. Now, there is an operation in set theory, which is called the Cartesian product or the Cartesian cross. And all it's denoted by is, let's say you've got some set A and some set B. The Cartesian cross or the Cartesian product is just that, A x B, or A cross B. And this is assuming, again, that A and B are sets. Hopefully you can see that. I hope there's not too much glare. And so what this means is, let's say that the set A is equal to, and this is how you sort of show that it's a set, by the way, is this curly brace. Let's say that A is the set of numbers 0, 1, and 2. All right, and let's say that B is the set of numbers 1, 2, and 3. Now, what the Cartesian cross here does is it creates a set of tuples of each element in set A crossed with set B. And so a tuple is just an ordered list of numbers. And so when we cross A with B, the resulting set A cross B is equal to the set of, again, the tuples, each element in A crossed with each element in B. So the first element of A cross B is going to be this first element here and the second element in a tuple, or an ordered pair in this case. And so that is, of course, 0, comma 1. And so this whole ordered pair is the first element in this set. Next up, we'll have 1, 1, then 2, 1, then we'll have 0, 2, 1, 2, 2, 2, 0, 3, 1, 3, 2, 3. So hopefully that makes sense. I'm not going to write it all out. But yeah, so that's what the Cartesian product is in sets. And there is one other piece of notation that we will need to understand. And that is if you cross a set with itself. So for example, take our set A again. If we cross A with itself, this is just the same thing as saying A2. It's not A squared because a square implies a typical exponent and an exponent is scalar multiplication. And this is not. This is set multiplication, right? So this is A2. And so if we think about our set R again, we think about our set R, that is all real numbers. So if we have R cross R, or again, that is R2, what does that mean? Well, let's make our number line again here. So this is our real number line, and we've got 0 here, and we've got all of our numbers up to infinity, and then to negative infinity over to the left. Now, if we cross R and R, let's just think about this for a second. So we will get each element in R crossed with each element in R. And so you'll have, all the way down here on this end, you'll have negative 9,999 crossed, negative 9,999, and you'll have that crossed with every other number. And we can sort of visualize this if we add another number line going this way. So we'll get rid of the 0 for a second here. We add a number line going this way, and it goes up to infinity up here and down to negative infinity down here. Now we can pick any point. So let's say again that this is 0, and this is, so it's 0 on our first number line, and it's 0 on our second number line. So we can call this point 0, 0. And let's say that this is point 1 and this is point 4. Then we have the point 1, 4. Because we have our first set crossed with an element in our second set, and that will give us that tuple, that ordered pair. Now, what this tells us is that R2, R crossed with itself, is the same thing as the Cartesian plane, which sort of makes sense, right? Cartesian cross, Cartesian plane, Cartesian coordinates. It makes a lot of sense, but that's really cool. So when we say that there is some element in R2, all that means is that there is some tuple, some ordered pair that exists in 2 dimensions. And so this applies for real valued things such as an ordered pair, but it can also apply to vectors. So let's say you have the vector I hat plus 4j hat. That also exists in R2 because it is essentially an ordered pair. That's how we name that vector. All right. So with that in mind, let's talk about this notation. So this, let's think about what this means. We've got our function f, and what this says is that we are taking an input in the real numbers and we are mapping it to an output in the real numbers. So what this means is, because this is just R, it means we've got our input number is just going to be one-dimensional. And so what this is saying effectively is y equals f of x. If we say that x is an element in R, we'll say that y is our output in R. And this is just the definition of a function. For every one input, we get one output. So what if we say f is a function which maps an input from R2 to R. What does this mean? Well, that would tell us that we've got some output, and now this is where we probably don't want to use y, because if our input is 2 dimensions, this tells us that our function is f of x, y, right? This means we are taking an element from R2, so an ordered pair, this tuple xy, and we are mapping it to R, so just a one-dimensional output. So we can go ahead and call that z. Depending on where you go, or well, actually no matter where you go, you will probably see the notation which is x1, x2, or f of x1, x2 equals x3. This is more useful because once you get to fourth dimensions and fifth dimensional functions, you sort of run out of letters here. We're at the end of the alphabet, right? So this is fine, but today we're going to stick with just 3 dimensions at most. So yeah, what this tells us is that our function f maps our ordered pair, our tuple from R2 into R. We take a 2 variable input, we get a 1 variable output. Now we can further generalize this to apply to all real valued functions and all vector valued functions. And so it seems this seems more intuitive when you map R to R, or R2 to R, or R3 to R, or R4. You map Rn to R. That means you have whatever variable input, right? So you have x squared plus y squared plus z cubed plus a to the 4th. And I know I said we'll be sticking to 3 dimensions, but this is, again, just for any arbitrary Rn mapping to R, and that equals, x4, right? And so we've got x, y, z, and a as our inputs, and so what this would be is, and let's say that this is, our function of x, y, z, and a, then what this tells us is that our function f is mapping from our 4, because we've got 4 variables, and it gives us a single variable output, so R, right? So this function f maps from R4 to R. We've got a 4-dimensional input, a 1-dimensional output. But once again, we can generalize this further to apply for vector valued functions as well. And so this seems a little less intuitive, but if we have, for example, f, or with vector value functions, you'll typically see a instead of the lowercase vector functions are usually, or matrix functions are usually defined with a capital letter. So let's say that we've got a, and that is mapping from Rn to Rm, right? And so this seems a little less intuitive, because we're going from some n dimension to some m dimension. How can we take some input, regardless of how many inputs it is, right? Whether it's 1 input, 2 inputs, 6-dimensional input, how can we get a multi-dimensional input out? And you might think, well, if we've got like x squared plus y squared equals, I don't know, z plus b. Okay, sure, that would work. That maps, some 2-dimensional input to a 2-dimensional output. Okay. But what this is typically used for, again, is vector functions. And so, for example, you might see some vector. I'll use this notation. You may see vectors denoted like this. Both of these are acceptable notations, whether you've got the sharp edges, the greater than, less than, or you've got square brackets. But so let's say that you've got some vector, and that is x1, x2, down to xn, and you are mapping it to x1, x2 to xm. So assuming that n and m are not equal, you are taking some vector as your input, and you are getting a vector with a different length as your output. And so this can be done a few different ways. And in fact, this notation works for different types of vector functions. So for example, let's say that we have a vector in fact, let's say that we're mapping from R to R3. Let's say we're mapping from R to R3. And so this can sort of be interpreted in different ways. The first way that I would think about it is you've got some vector and you've got a one-dimensional input, right? So S, and then you've got, I don't know, S squared and 3S. So S is our input. And when you plug in one value for S, again, it's single valued, you will get a three-dimensional output. You'll get, let's say S is 1, you'll get 1, 1, 3. So that is a three-dimensional output using only a one-dimensional input. But this notation doesn't only work, and of course, if you've got something like x plus y and 2x and x to the y power as your vector, this of course would be mapping R2 to R. So in effect, the same thing. But this notation, Rn to Rm, is more common when you have a matrix multiplied by a vector. So let's say that we have a matrix A, right? So again, our vector function's A. And let's say that A is some matrix, and let's just call it 1, 2, 3, 4, 5, 6. So A is our matrix of 1, 2, 3, 4, 5, 6. And let's say that we multiply it by some vector, I don't know. Let's see, we've got, let's just say 2, 1, all right? So we've got a 3 by 2 vector here and a 2 by 1 vector here. So if you don't know to do matrix multiplication or vector multiplication, you first need to see if the two matrices can be multiplied, and you do that by seeing if the inner digits are the same. And so the number of columns in one has to be equal to the number of rows in another. And your output is going to be the outer numbers, or at least it's going to have the dimensions of the outer numbers. And so let's just do this one real quick. We've got 2 plus 2, we've got 6 plus 4, and 10 plus 6, right? And so this is our new matrix, and so we can go ahead and just fully solve this out. 4, 10, 16. And so this is 3 numbers. So we just mapped a vector from R2 to R3. We took a 2-dimensional input and we got a 3-dimensional output, right? So hopefully that helps you understand it better. This function notation can be pretty confusing some of the first times you see it. You might see it in linear algebra. You may see it in, I don't know, real analysis or proofs or something like that. But yeah, so this is it's just a generalized function notation. It tells you how you are mapping an input to an output. You'll certainly see it in multivariable calculus because you do so many functions where you take a multiple input, you get a single variable output, or you do a lot of vector functions in multivariable calculus. So you will take a multivariable input, you'll get a multivariable output. So yeah, hopefully this helped you. If you were confused about what that notation meant, hopefully it helped. And yeah, I hope you guys enjoyed, and I will see you next time. Bye.